if I had to say, what do you need to know from yesterday? You need to know how to solve this equation symbolically, using the notation, the Cramer's notation solution. You need to know how to substitute the columns and come up with the solution. And then we let the computer do the work. And then, if you remember, we label the modes. We said that the longitudinal had particular modes that we always label. Short period. And the short period was the fast, rapidly decaying oscillation of the poles that are far from the origin.
And we're going to do what's called a short period. So I'm going to pulse the stick. And we're going to kind of look outside and see what it looks like out looking out there, okay? So I'm going to pulse the stick. Here we go. Oh, and look at this, the oscillation. See it? See it dying out? See how it dies out? Kind of oscillates and it dies out, like so. So you can change your airspeed. Yeah. These are the routes that are far from the origin. They're far from the origin. They're way off. If this is the J omega axis, these routes will be out over here. So they're going to be kind of fast. And so let's see what happens. I'm going to do the same thing. I'm going to pulse the stick. I'm going to give it a plus and a minus stick. We're going to kind of float. There's the oscillation. So it's just dying out. So we can take our data and look at it and then backfill an equation of what those short period routes would look like.
Then there's poles that are close to the origin, and those poles are the phugoid poles, long period poles. That's the exchange of kinetic and potential energy. So I'll fly this afternoon, and I will try to put some of those on a GoPro and maybe put it on YouTube, so you can actually watch those short period, what it looks like from the air. Okay, I'll actually do it.
If we're doing a phugoid, then instead of giving it a stick pulse, I would give it a throttle pulse. So watch, I'll show you. We'll give it a throttle pulse. So, notice how the airplane wants to climb now. See that? So I'll reset the throttle. And we'll just let it go and see what happens. So I'm letting it go. And the airplane, as it slows down, now wants to go down. But notice how much slower the oscillation is. Yeah. It's much slower than it was in the... So our route for the phugoid is much closer to the origin. The oscillation is much slower. Angular oscillation. We're exchanging kinetic and potential energy. So now we've got minimum max potential energy. Now the airplane, see, and it's doing it by itself. It's going up and down totally by itself. Exciting this phugoid. And it could go on for a long time, because the period could be 30, 40 seconds or whatever it is. Oh wow. But that's the short period routes and the phugoid routes. Okay, you got it? Yeah.
Lateral mode's the same way. You're going to get a set of these for the lateral mode, except the lateral mode is going to have a roll mode time constant, how fast the airplane rolls.
Okay, so I'm going to do one more turn. We'll do one more turn. I'm going to do a little faster this time. So now we're at 120. We're going to go into a right 45-degree bank. I'm looking to make sure there's nobody out here. And then from this 45-degree bank, I'm going to go a step input right now. See that? That's the roll mode. So that roll mode depends on what's called LP, the roll damping. Okay. So the roll damping stability derivative, if you increase that, it would slow down that roll mode time constant. So I could simulate a larger LP. If I had a larger LP negative, it's always negative, but if it had a larger value, then the roll mode might look like this. See how slow it's going for the LP? Yeah.
And it'll have a Dutch roll, which is the drunken Dutchman coming home from the tavern, walking down the ice tunnel and going home, right? It wasn't an ice tunnel. I can't remember what Roscoe used. Whatever they have in the Netherlands.
So the last maneuver we want to demonstrate is the Dutch roll, okay? All right. Then you give this thing a rudder input, and then you just watch the oscillation. So my hand's off the air, and here goes the rudder input coming in. So you just let it. See how it's dying out? See how it's oscillating left to right? Yeah. Now we're not getting much rolling, so that's called a phi to beta ratio. That if you had rolling on it. So this airplane doesn't have much phi to beta. So I'm gonna do it one more time. So we'll get the thing all set up equal. Now here's our input coming in. We'll get our input going like that.
Holy crap!
Yeah, so let it die down like that. And so you see, and now those roots on the S-plane would be like way over here. Dies out kind of fast, right? That's called the Dutch roll. And a big airplane, you can imagine what I'd be doing to the people in the back.
Tossing them around
Yeah,
all over the
exactly.
place.
And then the spiral. The spiral was a mode close to the origin, which says whether if you fall asleep, you will wake up or you won't wake up, right? You either slowly go back to level flight and keep flying, or you'll slowly roll off into the drink. And that's that pull right close to the origin.
We could show the students spiral mode. I'll let you demonstrate the spiral mode, okay?
All right, that'll be fun.
So go level flight like this, right there. Right there. Now put 10 degrees of bank either way. 10 degrees of bank either way. Right? Right. Now let the stick go. We're just going to let it go. Uh-oh. Looks like our spiral mode is unstable. See that?
Yeah.
Our spiral mode is definitely unstable. Okay, you can take it back. Okay. So it's unstable to the left. That could be because of the engine.
Okay,
So let's, yeah,
going
so,
it that way?
yeah, so let's go unstable. Let's go to the right. Do 10, yeah, now just let go of the stick. Let it go. Let's see what happens. It looks like it's coming back to the left, isn't it?
Yeah, it's working back
Yeah, so
that way.
it's probably the engine that's causing
motor?
it doesn't matter, it still would put you into the drink. But if
Yeah.
it was a real aerodynamic unstable mode, we would roll off to the right as opposed to the left.
So notice how we've named the poles. You've named the poles. You also, with airplane analysis, will name the zeros. You'll name the zeros. And the last thing I want to show you before we start actually using this stuff is today, right now, is to show you how these names of these poles and zeros come about. How do they come about? Because I want to control this oscillation. I don't much care what happens to the phugoid. I do, but say I didn't. Can I just control the short period? Or can I just control the Dutch roll, right? Well, it turns out, for most practical applications, you can build control systems to just do that. And then keep your fingers crossed that you haven't screwed up the other poles and zeros, okay? You just try it, because it's going to be a real quick fix. So, if you just wanted to find the short period poles and modes, you would circle these terms, and you would make a 2x2 system that's shown in the upper right-hand corner of that plot. You see that? And that 2x2 system would give you the short period frequency. It would give you a set of complex poles that would be very close to the short period poles for the whole system. Look what's hidden in there. What is MQ? Got a name, right? Pitch damping. It comes from CMQ. It's the pitch damping. It's the restoring moment. If I ever see a pitch rate, it's the restoring moment. Look how instrumental MQ is in deciding the damping. Do you see that? So when you're building an airplane, you're sharing lunch with somebody, you're sharing lunch with them, and they say, well, my tail that I picked out is going to have a larger MQ. Well, what's the effect going to be on pitch damping? And you discuss these things. You know, you're not going to the computer and seeing and looking. You're having lunch. Most of these great systems are designed right at lunch on a napkin. You could talk about the MQ effects on the damping of the short period load. Or you could talk about the center of gravity effect on M alpha. That's the longitudinal static stability derivative. What is the center of gravity effect on the natural frequency of the short period? Do you see that? If I move the CG forward, I'll have too fast a frequency. I'll oscillate faster even. So you get enormous insight into what these things are doing from your design. You're designing these. You're building the tails. These things are coming out of the geometry of your design. And with these approximations, you can estimate the effect of them on the poles. And if you understand how the poles work, then you can see the time response of your airplane. And you can do all of that over a lunch table and over a discussion. Now, do aero engineers talk like this in the real world when they're working? Absolutely. I have never been anywhere, working anywhere or in any company, where you didn't sit down and talk to engineers and they talk about CMQ, M alpha, the damping derivatives. It is part of your vocabulary. That's why these stability derivatives from coefficients is so important. And then do you see how simple I can make these couple differential equations so that you can talk intelligently about how the airplane's going to respond within each mode. You see that? So this is called the literal factor for short period.